Thanks to the organizers for the invitation and for organizing this, and ICTS for providing such a beautiful, fantastic venue where in every corridor and at every turn there's a chalkboard, so you can have a discussion. So I'll start out with just a few slides to set the context and then switch to the chalkboard for the rest of the 4.5 hours. There's also a tutorial on Tuesday where we will do explore discrete exterior calculus and finite element exterior calculus using the Python library. So discrete exterior calculus, also known as DEC by its abbreviation. I just want to tell you where it fits. So that has to do with these two words, structure and compatibility. And the word compatibility, I first saw in this conference in 2002 at IMA, which is was one of the NSF Math Institutes. And so I had a poster there as a grad student on discrete exterior calculus. And so this word compatibility will become clear, but notice that this was only spatial discretization. So this is 2002, and this is maybe 17 years later, there was a semester-long program at the Newton Institute in Cambridge, where geometry was recognized as an important part, and then it was now computational differential equations because people started thinking about time-dependent problems also, not just spatial discretization. So this was a really wonderful program, just ended before COVID started, and I'm glad that it was not in 2020, otherwise our lives would have been very different. So again, the word compatibility appears here and the structure preservation appears again. And this compatibility has to do with this idea that if you're using in mixed formulations in finite elements, when you have two variables or multiple variables, then it's important to choose the spaces for the different variables in a way that's compatible. For example, on the left, it's just Poisson's equation and used in the direct form, not in the mixed form. And if you solve it using finite elements with, I believe, Lagrange second order for Lagrange second order for so piecewise constant. So this is Lagrange second order, and it works perfectly fine. There's no problem. And this is, by the way, an experiment that's in a recent paper, very nice survey paper by Kaibo-Hu. And then on the right, if you do the mixed form, so you can think of this as D'Arcy flow. Velocity is negative gradient of pressure. U is the pressure, sigma is the velocity, and divergence of velocity is the right-hand side, the source term. So here he has picked piecewise constants for the pressure, and he has used Rabiat-Thomas elements or Whitney forms for the sigma variable, which is the velocity. So that's represented as fluxes through the edges. And you can see that it gives a solution which is looks close to the original. And if you refine, you get nicer solutions. So here he has used nodal finite elements where the vector field is the pressure is still piecewise constant, but the vector field is represented as two components at every vertex. So it's nodal finite elements using Lagrange. So that is unstable and gives bad results. So this is the idea of compatibility, that when you're doing mixed formulations, then you have to use the spaces in a compatible manner. So there's a whole theory of that. There are other structures that you want to preserve. So here, this is for Poisson's, the vector Poisson's equation. And in this case, the topology of the domain is important. And in this case, this happens to have a hole. So it will have what is called a harmonic form. And on the left, it's using Lagrange. So this is from a paper, very famous paper by Arnold, Falk, and Winter, which appeared in 2010. And before this, there was a 2006 paper which started this field or made it popular, this finite element exterior calculus, or FEEC, F-E-E-C. So on the left is Lagrange finite elements with two components for every vertex to represent, and that's dominated by something that looks like the harmonic form, and it completely misses the true solution, which is on the right, which is done using Rabiat-Thomas or Whitney forms. So one has to sort of take care of other structures. And in this example, this is the curl problem. Curl of U is lambda U, and divergence of U is 0. U is a vector field. So this is like the Poisson problem, but because the divergence is 0, it only has the curl term. And if you compute, so this is the Helmholtz problem. If you compute using Lagrange finite elements, 2 for every vertex to represent the vector field, and you find the eigenvalues, you get something that looks wonderful, but is completely wrong because you can compute it by hand, and you will see that this has discrete eigenvalues. And the one on the right is again done using Whitney forms or Raviathoma, and it gets the eigenvalues right. So the other component, so there is this, so the idea is that one should try to think about the structures, the mathematical structures in the equations that one is trying to discretize. And the other component is, and then of course compatibility when you're doing multiple variables at the same time. The other component that has been very helpful is exterior calculus, which is a generalization of vector calculus. And it's not essential to use it, and I'm not trying to say one should or not, but it does help in, so this is again by Doug Arnold and Anders Log. They made this really beautiful poster of the the periodic table of the finite elements. And so it allows you to kind of talk about everything uniformly, and you can go to any dimension, and you can do things on a manifold. So it becomes very nice and easy to talk about things in a unified fashion. So this left column is this famous PR minus lambda K family, which for R equal to 1 is the Whitney forms invented inadvertently by Hassler Whitney, who was a geometer in the 1950s. He wrote a book in which these appeared. And then many years later, computational electromagnetism people, I think specifically Bossavit, who used to work for the electric company in France, and he was a student of a famous numerical analyst. So he realized that what Whitney has invented was really needed to represent electric fields and magnetic fields. And so these are the n equal to 2 and 3 case. The first row in each is the Whitney forms, the classical old Whitney forms that Whitney had invented, which has very nice problems. And then in the next lecture, I'll at least introduce you to those, even though those are not directly related to DEC, but in a way they are, if you want to prove anything about convergence and stability. But so the first one is Lagrange. And if you just focus on the first row, you notice that there is a degree of freedom for every vertex. There's a degree of freedom for every edge. And there's a degree of freedom for the triangle. And similarly, in the first row, in the tetrahedral case, there's 4 for the for the first case. Then there is 1 for every edge, 1 for every face. So these are Nedelec edge elements and Nedelec face elements, and that's DG, discontinuous Galerkin, piecewise constants in the last. So somehow there's this geometric thing that for every important geometric feature in your mesh, there is a degree of freedom. So for example, the degree of freedom might be in the case of, let's say, the red square in the first row could be the line integral of the vector field. So if you want to discretize it, you will do the line integral of the vector field along the edges. So this idea has really flourished and continued. And this is from the same paper by Kaibo. So here he's showing how to go beyond Laplacians and how to do many different physical problems. And for example, in the middle, you see elasticity, and this notation of lambda 0, 1, 1, 1, 2, 2, 3, 2 will become clear in the third lecture. But on the top corner are distributional elements. On the left bottom corner are finite elements, polynomials. So for example, for elasticity, you can do Lagrange, then you get Reggie, which is piecewise constant metrics, and then the incompatibility operator brings you to something which is distributional because you've taken 2 derivatives. So anyway, I don't want to dwell on this too much, but just want to mention that DEC has continued to develop, and we recently had a conference in the new Math Institute, which is in Chicago, relatively new. It's 5 years old, 5, 6 years old. And so this, we had people from, so we had physicists, engineers from around the world. numerical analysts and differential geometers. And so it was very nice collaborative discussion, and many new things got started. So, okay, I think I will stop the slides here and switch to the. Any questions so far? So let me see if I can, let me see if I don't have to cheat and look at my notes, but forgive me if I do. So the first one, so the one thing you can think of it as a DEC as is that, okay, it's only working with degrees of freedom. There are no shape functions. So many of you are familiar with finite elements. So DEC is a framework in which you only work with degrees of freedom. So naturally, you might say, okay, what do you do if you want the solution somewhere else? So in DEC, like in pure DEC, solutions live at vertices, at edges, on triangles, in the tetrahedra, depending on which variable you're talking about. But you can use shape functions, in particular the Whitney forms, because DEC has the same degrees of freedom as the lowest degree Whitney forms that you saw in that periodic table, where there was one for every important mesh element. Like there was one for every vertex, one for every edge. So you can use those shape functions to interpolate everywhere and compute L2 norms and H1 norms. And in fact, the convergence of let's say, the solution to the Poisson's equation for DEC uses that technique. It's a very recent paper. So there are two recent papers which prove convergence using different techniques. And one of them uses this interpolation using the Whitney forms to get a solution everywhere so that you can compute L2 norms and compute errors in an L2 sense. So DEC is something which only works with degree of freedom, and that's what you will see. So let's see. So maybe I'll start with this idea in vector calculus that you could have, if you start with functions and do a grad, you get vector fields. Then if you do a curl, you still get a vector field. And you do divergence, you get functions again. Some people like to call those densities. But so one important feature of vector calculus is that curl of grad is 0. And that divergence of curl is 0. So if you're trying to build a discrete theory, then if you're trying to discretize the differential operators and you say, here's my curl and here's my grad and here's my div, then it had better be that this property is satisfied. So this is an example of a differential complex. So this property is called the complex property. And the generalization of this hides many wonderful things like harmonic forms and topology. But to do that generalization, I mean, one can do with vector calculus, but it becomes very, very nice if one does it in the most general way possible using smooth manifolds and exterior calculus. So, but the thing is that it would take too long to go through the smooth theory to get to a stage where we can talk about the discrete stuff. And my goal is to get to the discrete stuff as fast as possible. So I thought one compromise I can do is to treat each object in the smooth theory as a black box, but whose properties I will describe, the important properties. The structures of that smooth object, we will try to write down without having to define exactly what that's, so like, this is how the operators interact with each other, and these are the important properties. And then we'll try to preserve that structure as much as possible in the discrete world. So for example, if I was to really start, like do a whole thing from smooth exterior calculus, I would have to say, M is a smooth manifold, what does that mean? So for all of these, there is of course intuitive pictures that you should have in mind. Just think of a smooth surface, for example. But to like properly define it, Lee has a series of 3 books totaling about 1500 pages. You have to start with topological manifolds, smooth manifolds, Riemannian manifolds. And the reason it takes so long is because there's all this background. So you would need to say, oh, manifold is a second countable Hausdorff space, which is locally Euclidean. Okay, what does locally Euclidean mean? You need to define charts, transition functions, homeomorphism. So there's too much machinery that we would never really get to the discrete stuff. And I think one of the beauties or one of the good things about the discrete stuff is that it really requires minimal background, which can actually work against it, because sometimes people play the game that, look, I'm doing something so complicated that you can't understand. But when you're doing DEC, you don't play that game. In fact, a few years ago, we just, as an experiment, took some high school students from 9th, 10th, and 11th grade. And by the end of 1 month, they did diffusion equation on a torus embedded in R3. So it's fairly easy to describe all the concepts in a very self-contained manner, which, like I said, is a double-edged sword, because it makes it look like you didn't do anything interesting or deep, but it is easy to understand. So I won't define exactly what a smooth manifold is. Let's see. Some of the terms that will show up during the course or the course of lectures is this symbol, the tangent space at point P of the manifold. So again, have a picture of a tangent plane for an embedded surface, but all of this can be defined without embedding, and it can all be defined very nicely intrinsically. Then there's a dual vector space. Then you glue them all together and you get a tangent bundle. And so to do that properly requires to talk about what is a vector bundle and what does it mean to glue them together. But you can just think of this as a tangent space at every point. And so that when you want to define a vector field, you will pick one vector from every point from this tangent space. And similarly, there's a cotangent bundle. So this is the vector space dual, means these are functionals which take tangent vectors and produce numbers, and they're linear. What else do we need? So I think, so the other thing we need is, like, the main actor in this whole picture is differential forms. So K will be a number. So M will be something which will have a dimension N. And K will be a number between 0 and N, an integer between 0 and N. So the space of differential forms on a manifold M is often the notation that's used is this one. Many numerical analysts don't like to use this because omega is the domain, but we are trying to revolutionize the field and use omega. Many people you will see will use lambda kn. But so how do we talk about differential forms without talking about differential forms and without defining all of the machinery of exterior calculus? Well, like I said, we'll think of them as black boxes. I will say some words and then give the properties, and then we'll try to discretize. When we talk about the discrete version, we will try to see if those properties were maintained or not. So a differential K form is a antisymmetric. It's a field of antisymmetric tensors. So for any vector space such as TPM, you can define tensors, which are objects which are multilinear. So they take some number of vector arguments. They can also take covector arguments, but so they can take things from here and things from here and produce a number, and they're linear in each slot. But these ones are they take purely vector arguments from the tangent space. And they produce a number. It's multilinear, so the properties are that it's antisymmetric, it's linear in each slot, and this antisymmetry turns out to be a really magical property. Like, you would think, why would antisymmetric tensors be important? But it turns out that tensors are, differential forms are really useful in integration. And in integration, if you change the orientation, you get a negative sign. So for example, yeah, so they capture that idea in the antisymmetry. And some of the, I have heard from some physicists and engineers who've started using or have been using differential forms that the reason they like differential forms is because it's more physical in the sense that when you make a measurement, you really don't do a vector field measurement at a point. If you're measuring, let's say, a fluid velocity, what you will probably measure is flux through a small patch and then use that as a proxy for the vector at that point. If you're measuring electric field, there is no instrument that will tell you the electric field at a point. I think what you'll do is probably push a charge for along a small curve and see how much work was done and then infer the electric field from that. So I'm not a physicist, but that's what I've heard, that they really, they capture the idea that measurements are done on integrated quantities. So differential forms are the right language rather than vector fields. And we just happen to be, so there are several good features. One is that you will see that no metric is introduced until the next lecture. And when you read, the reason there are 3 books of Lee's is because the middle book is smooth manifolds, which doesn't require any metric. And the 3rd book is Riemannian manifolds, which introduces metric. But actually, it's not entirely true. You actually do need metric if you want to do PDEs. So we will introduce metric earlier. So this first lecture is metric free. The second lecture will introduce metric in a discrete way. And we will talk about the Hodge-Laplace problem. And the third one, we'll try to do differential geometry and discrete curvature and things like that. So yeah, so they are antisymmetric tensors, which are linear in every slot. So if, let's say, alpha is a K form, then it's a field available everywhere, and at any point you can feed it vectors in the tangent plane at that point and get a number out of it. So these are real valued. So it's important that they are real valued. In the 3rd lecture, we'll introduce vector valued, which is what you need to do differential geometry. So let me write this notation for vector fields, math frac M. So this is smooth vector fields on a manifold. So just imagine some smooth vector field on a surface, for example. So if alpha is something like this, then if I take, let's say, K vectors, V1, let's write Vi, Vj, Vk, then this will be a number, and this number will switch sign if you take any, so these are dots. If you take any pair such as Vi and Vj and swap them. So you pick up a minus sign. I think I won't say anything more about that, but some examples of forms are electric field is a 1 form, magnetic flux is a 2 form, velocity can be represented in a proxy way as either a 1 form or a 2 form. In a fluid case, generally it's represented as an n-1 form. So a 1 form in 2D and 2 form in 3D, which captures the idea of flux through the shared faces. Right, so let's see. So manifolds are where all the action is happening. These K forms are the things which are the main actors. And the main operator is the exterior derivative. So this is something that, it's a derivative that produces antisymmetric tensors of 1 degree more. And it has the key property that d square is 0. So if you do it 2 times, you get 0. So there are several ways to define it. One possible path is, but I won't define it because we will just do the discrete version, and you'll see it's super simple to think about it discretely. But we'll try to maintain this property that it takes whatever discrete thing we choose for this, it takes to the discrete version of that, and that this applying it twice gives you 0. So we'll try to maintain that property. But the two typical things you will see in a textbook, and I should speed up, are you define derivations, then define differential using that, then use coordinates, and then prove uniqueness and say, okay, I found an exterior derivative which satisfies certain properties. Or you can do what is called a Palais style. Richard Palais introduced a definition which is completely coordinate free, involves Lie brackets. And again, you have to define derivations, Lie brackets, and so on. So we won't do any of that. So we want to discretize. So the punchline is we'll discretize manifolds as simplicial complexes. And so that is what I will try to quickly define. So the discrete things we'll try to do via examples as much as possible rather than formal definitions, but once in a while we might do. So for those of you who are experts, who have done courses in manifold theory or differential geometry, you should be happy that I'm skipping that stuff. If you've also done courses in algebraic topology, then unfortunately you will be bored for a little bit. But hopefully you will see it in a new light. So this will be replaced by what are called cochains. And these are the terms or things that I would want to, and then D will be replaced by coboundary, which I will also do, but we'll just use the same symbol because we don't work with the smooth stuff. So we like to use the smooth symbols for our discrete world. So a simplicial complex. So let's start with that. But this is something that you're all familiar with. So first of all, there's a simplex. So all the people who do finite elements, a triangle mesh is a simplicial complex. A tetrahedral mesh is a simplicial complex. A simplex is something that you get by taking a K simplex requires K plus 1 points, which are in general position, meaning that like if you take one of the points as the origin and take the vectors to the rest, then those form a linearly independent set of vectors. And then you take a convex hull of those points. So for example, you take 3 points which are not collinear and you get a triangle, and 4 points which are not lying in a plane and you get a tetrahedron. So I hope, and I'm sure that I don't need to formally define what a simplex is. It's a triangle or a tetrahedra or whatever. And a simplicial complex is a triangle mesh that you use in your computations, tetrahedral mesh. But the main thing to note is that often we tend to use for PDEs some special type of simplicial complexes. But here are, so maybe I'll just say the definition and not write it because otherwise I'll run out of time. So the definition is that, first of all, there's the idea of a face of a simplex. So a simplex is defined using these points, right? And if you delete 1 point, you get a K minus 1 dimensional face. If you delete 2 points, you get K minus 2 dimensional face. So if you take any subset of the vertices, you will get a face. And the whole simplex is a face of itself also. The others are proper faces. So, so simplicial complex is one in which if a simplex is in that complex, its face, all the faces should also be included. So it's that structure. And if 2 simplices are in the complex, then the intersection should be a face of both of them. So what this allows is many things. So for example, certainly, let's say if I take these 2 triangles, this is a good example of a simplicial complex, but something that you typically won't work with in most computations, but nowadays people are starting to do things like this. So this is also a simplicial complex, even though you won't typically do a PDE on it. But so this is okay, this is okay. Here's something that is not okay. So if I take these 2, then their intersection is not a face of both of them. The intersection is this part, which is neither a face of this nor a face of that. You're not allowed, so this is not okay. You are not allowed something like that. Again, because the intersection is this region, which is not a face of both of them. You're also allowed, yeah, so all these are valid things. So, but often we will work with, unfortunately here there is no getting around the word manifold, but we will work with some continuous, not smooth, but continuous manifold, which we call, we'll just say manifold simplicial complexes. Because we want to do PDEs, and PDEs are done on domains like this, not on domains like that, typically. But of course, there are examples in which that is also useful. So these will be things which will be like, that example is okay. I'll just say by example, but this is not okay. And neither is this. So none of these are manifold simplicial. But something like this, where you have triangulated this region, is perfectly okay. So this is okay, that's not okay. And I think that's probably all we need. So simplicial complexes will be our discretization of the manifold. It will be the thing where our things will live and our operators will act. So then I should mention what are chains. So once again, I don't have time to write, but so you can take chains which are integer valued, real valued, and often people will put, for example, R or Z. So these are basically a finite, our simplicial complexes are always going to be finite, so don't need to say that. These are formal linear combination of simplices, k simplices. The coefficients are integers or reals. So on a computer, you can represent a k chain as a vector with either integer entries or real entries, and these are the entries are corresponding to each k simplex. So for example, you may have, let's say, this triangle, and you have vertex 0, 1, and 2, and you could define a one chain, an integer valued one chain, which takes the value, which is a linear combination. So let's define a chain C, which is +1 times this face. So let's orient these guys. Let's say plus or minus 1 times 1, 2, and 0 times that. So it's a linear combination with the coefficients are integers. And you can use any integers, but typically you only need 0, 1, and -1 for our purposes, because, yes.
Yes. I have a question. So the faces are, I mean, all the simplices that they are oriented?
Yeah, I forgot to mention that. So let me mention that. Yeah, thanks for reminding me. So a simplex is this collection of general position points and the convex hull of that. An oriented simplex is a simplex plus an orientation. And that orientation is given in the following way. It can be done in a completely combinatorial way. And so we'll say oriented simplex is a simplex plus a vertex ordering. So you provide a total order on the vertices of the simplex, and by listing the order that you want, you orient the simplex. And so there are two possible orientations. So for example, let's take 0, 1, 2. So if you do all possible permutations and look at the sign of the permutation, meaning how many swaps you need to get it in that position, then, so this is a plus sign, this is a minus sign, that's a minus sign, this is plus, and that's a minus. So, so I can write the orientation. If I write 0, 1, 2, that's the same as, so 0, 1, 2 is the same as 2, 0, 1, because 0, 1, 2 and 2, 0, 1 are both positive permutations. So for any, so if you have a permutation pi, permutation of the vertices, then so we'll use this notation, square bracket and ordering, and the square bracket is a reminder that it's an equivalence class. So you can have other orderings which are in the same class, which have the same sign. So there will be either a minus sign or a plus sign, and those are arbitrary decisions. So if I have, let's say, V0, V1, Vk, and I do, I want to compare its sign with the permuted. So then this will be sign of the permutation, where the sign is how many swaps are needed to bring it into the identity permutation. So yeah, so we will be working with oriented things because that's what you want to do PDEs on, although you can do integration on non-orientable manifolds, but that's what we will work on. Yeah, so chain is just a formal combination, and we will work with oriented simplices starting from this point on. And so the chain is supposed to be the domain where things are happening. So by listing, so for example, by listing this and this, what you are singling out is this guy and this guy, but oriented in the wrong way, in the other way, because that's what you chose. So any questions about all of this? So the differential forms will be discretized as cochains. So the space of K cochains which we will write. So we will only use real valued. So I will not write the R. And these will be duals to the chains. So the chains form a group because the values are in a group. They form an abelian group. You can add chains, you can subtract chains, you can. So these are. So this space is the set of homomorphisms from the chain to reals, which means if this was real valued chains, we wouldn't have to use a fancy word. We could just say these are linear maps from the chains to reals. So yeah, it's just the dual space. And so an example of a cochain is, let's say if alpha is a one form on some manifold, then you could define, and you have a triangulation of the manifold, and you leave the slot open, and let's call it alpha hat, and you can define, for example, alpha, which is a one cochain, let's call it X. Because if I give it a chain, it's a set of a linear combination of edges, integration is linear in that slot, I will get just the sum of the values that you get by integrating on those edges. If I change the orientation of the, I'll get a negative sign of those edges, right? So basically, cochains will be things that take numbers on, one cochains will take numbers on edges, zero cochains will take numbers on vertices, two cochains will take numbers on triangles. That's all. So we have our space, we have the main things. Then we want to define the exterior derivative. So the discrete exterior derivative will be defined as the dual of what is called the boundary operator. So the boundary operator is a map from K chains to K minus one chains. And we will just, so I'm going to use this notation. So if I have a cochain like alpha, then when I write this is not an inner product, but it's evaluation of the cochain alpha on the chain C. Because this is helpful when we think about the D being a dual of the boundary operator. So the boundary operator is defined on simplices, and then you can extend by linearity. So what it does is it takes, let's say, so the boundary of V0 through Vk will be summation I from 0 to K, then -1 to the I, and then the face, which is obtained by deleting the ith vertex. So you define it for simplices, and then you say, okay, chain is just a linear combination of the simplices. So extend this boundary to a homomorphism between this chain group and this chain group. And so, for example, If I have 0, 1, 2, then the boundary of this triangle 0, 1, 2, maybe I should use V0, V1, V2. So this will be, you keep deleting one at a time and put a sign. So -1 to the 0, delete this guy. So that's V1, V2. Then delete this one, minus sign, V0, V2. And then delete the last one, plus sign, V0, V1. So if you look at what these are, so let's orient them from low to high. But if you look at the boundary operator, it's saying it's V1, V2 minus V2, V0. So it's wanting you to go this way, that way, and then plus V0, V1 this way. So and this we have written as 0, 1, 2, so it's counterclockwise. So what it does is gives you the boundary, the induced boundary with the correct orientation. And if you did this, so a small exercise, try this for example, for these two. So let's say this is 0, 1, 2, 3. If you do this, this will be boundary of this plus boundary of that. And as you can, let's say both are counterclockwise, then what will happen is that it'll induce this way on that edge and that way on that edge, and those will cancel. And then you will end up with the boundary. So it captures the notion of sort of geometric boundary. And the exterior derivative is defined as, the exterior derivative will be defined as co-boundary. I was going by the tube lights, but I realized that they are in different places. So we'll define the co-boundary operator is a map that takes k chains to k plus 1 chains. Oh, co-chains, sorry. And so if I have some alpha, which is a k chain, k co-chain, then the D of that, and you can give it an index because it's a whole family of operators. So its value on a simplex, like, let's say, let's call it sigma. So it's the value of this. So let's say this is a k plus 1 simplex. This is a k chain, a k co-chain. So the D of the k co-chain on that is just defined to be the value of alpha on the boundary of this. So that's why you can do another calculation, like do another boundary operator. So this is one boundary operator. If you do one more, then the boundary of a disk is a circle and its boundary is 0. You will see that combinatorially reproduced. So if you do boundary square, you'll get 0, and it's not hard to prove. And that's why D square is 0, because if you do two Ds, they go over here and you get boundary square. And so we have captured the idea of orientation by using oriented simplices, the idea of a space by using the simplicial complex, the idea of differential forms by using cochains, and the idea of exterior derivative using this very simple operator based on the boundary. So very simple example is, let's take this. This is our thing, and F is a 0 cochain. So 0 cochain is just things that take values on the vertices. So we will have F0 and F1. So D of F will be a 1 cochain. So think of this as a 0 form. 0 forms are functions. 1 forms, 2 forms, 3 forms, then go on. So F is a function, a discrete function. And D of F is nothing but, it's a 1 cochain. So I should tell you what its value is on this edge. So its value on the edge, let's call it 0, 1, is the value of F on the boundary of 0, 1. The boundary of 0, 1 is 1 minus 0. So this is the value of F on that face minus the value of F on that face. So F1 minus F0. So it's simply the difference. And for a triangle, you should do this exercise. Yeah, you should do this exercise yourself. For a so take X to be this simplicial complex 0, 1, 2. And then take a one co-chain. So the one co-chain will be something, then let's give this an orientation, give these an orientation. One co-chain will be something that takes values on the edges. And its D will be something that takes values on the triangle. And you will see what it will be, if let's say the value on this edge is alpha 0, 1, the value on this edge is alpha 1, 2, and the value on this edge is alpha 0, 2. It will be just the sum of these with the sign taken care of. The sign will be whether the orientation of the simplex of the triangle agrees with the edge orientation or disagrees. So for example, in this case, if you work it out, you will see it's alpha 0, 1 plus alpha 1, 2 minus alpha 0. This is what you would expect from the definition. So we have a D whose square is 0. We have our forms. So let's see. Next thing, I guess one should talk about then is so I want to get to various properties that you see. So we have preserved a little bit of structure already. We have this D square equal to 0 structure preserved. So there are other things that are true for example, for the exterior derivative. So I want to introduce the objects that are needed. So for example, the product rule. So one of the most important things in developing derivatives, not one of the most important thing in addition to linearity is the product rule. If you study any sort of modern treatment of differential geometry, if it's axiomatic, they will just say you have linearity and you have product rule of a certain kind. So every derivative has some sort of a product rule. So but what does a product mean? So for product, there's this idea of a wedge product in smooth exterior calculus, and it's written like that. And if you have a K form, so this is the smooth world. If you have a K form and an L form, then their wedge product is a K plus L form. And so this is the structure we would like. And so what are the properties we'd like to preserve if possible? One is that it's bilinear. So it's linear in each slot. That's easy, almost by definition, we'll be able to get. Then there is this idea that if I swap them, I pick up a sign. So this is called anti-commutativity. And this has to do with wanting to have anti-symmetry in the resulting thing. And the last one is that if you take the product rule, so if you take the product of two things and do a D of that, that's the derivative of the first times the second plus, but now there's a sign, and this sign is K in this case, which is the degree of this guy, times alpha wedge. So the usual product rule we know from calculus, but written for forms. So if alpha and beta were both zero forms, i.e. functions, this will be your usual product rule, that the derivative of a product is the derivative of the first times the second plus K is 0, so plus first times the derivative of the second. So you had better have this, and you had better have, so D had better interact properly with this guy, and the wedge had must have that. And then there is another property, which is associativity. So let me just write the discrete wedge definition. Okay, what I'll do is, instead of writing the definition, I'll give examples to save time. So discrete wedge, I'll just write the words. It's an anti-symmetrized cup product. So cup product, so we'll be working with, let's say alpha is a K chain, and beta is N. K co-chain and L co-chain. Then, okay, might as well, let's see, how long will it take? Yeah, okay, let me just quickly write it. So the wedge product, the discrete wedge product, its value on a K plus L simplex will be summation. So there'll be a factor K plus L plus 1 factorial. And then there'll be a summation. There'll be a sign of permutation. The permutations will be for numbers from 0 through K plus L, sign, and then this will be alpha cup beta with the permuted. So I just want to tell you this in an example and this definition in an example, and then tell you how wonderful geometric, it has a very nice geometric meaning or definition or implication. So what is a cup product? So let's take two, so let's take alpha and beta to be 1 cochains on a triangle. So then the cup product is not actually a cochain, but we'll still evaluate it on 0, 1, 2. And it will be just the value of alpha on the first two, because it's a 1 cochain, so it needs, alpha needs an edge, and beta needs an edge, but we will sort of pivot on this common thing. So this will be beta 1, 2. So the wedge product will be built by just doing anti-symmetrizations of that. And so let's maybe do an example. So yeah, so let's do a very simple example. So first of all, the motivation, so the things in discrete world happen a little bit differently, and some things are impossible to preserve. So for example, in the smooth world, if I'm taking a function and multiplying it by a 1 form, I can do it at any point. But in the discrete world, the function lives on the vertices and the 1 form lives on the edge. So what does it mean to multiply them, right? It seems meaningless. But if you ask anyone, hey, I've got something that lives on vertices. Let's say you have an edge. I've got F0 and F1 living here, and I've got something that lives on the edge. Let's call it the value alpha 0, 1. How should I multiply them? Well, okay, a reasonable thing would be to average these guys and multiply by this number, right? And in fact, the definition that I gave you does give you this. So let's actually do this for this example. So let's say we are trying to do, we've got this situation and we want to do F wedge alpha. And so F is a 0 cochain, alpha is a 1 cochain, their wedge will be a 1 cochain. So I need to tell you how to evaluate it on the edge. So there's a factor 1 over K plus L plus 1 factorial. And this is 0, this is 1, so that's 1 over 2. And then you have to do F cup alpha on 0, 1. And then you have to use a sign. So minus F cup alpha on 1, 0. So these are the two permutations, 0, 1, and 1, 0. You have to run through all the permutations, put the sign, normalize, and do the cup product. Right? This is exactly the definition. So if you do this, the cup product definition gives you F on 0 and alpha on 0, 1. So let's just write this as F0 alpha 0, 1 minus F on 1 alpha on 1, 0. But cochains switch sign when you change the orientation. So I can make that a plus and change this to 0, 1. And then you get exactly that definition. So in fact, if you do this for a triangle, you should try this example. So take alpha a 1 cochain and alpha beta both are 1 cochains. And compute using this definition the value on a triangle. And you will find that you'll get some expression with 6 terms, which is just some algebraic expression with using all the permutations of 0, 1, 2. But if you if you see it, if you think about it, it will give you this structure. It will give you, so the value will be an average of this kind. Take alpha here and beta on these two, the average of the beta on these two. Take alpha here and the average of beta on these two, and alpha on this, and average of beta on this. So there exist appropriate orientation such that it can be written as, so you take the average here, so let me write this as 1/2 in blue, and then you do a global average. So, and for example, if you had a tetrahedra and you had a 2 co-chain and a 1 co-chain, you'd be taking the value on every face multiplied by the average of the 3 edges coming into the face, do that for every face and do 1/4 of the result. So it has a very clean geometric interpretation, which is called the averaging interpretation of the discrete wedge product, which at least for us was a recent discovery, but certainly people probably knew about it. So by the way, I didn't mention where we wanted to take this. So if you have this, then you get this structure, 0 forms, a D, let's index it, gives you 1 form, and you can start with a 0 map, which just maps 0 to 0, a linear map that maps 0 to 0. So you get this general thing which is called the de Rham complex. So each of this is a D, this is D1. So this is called a de Rham complex, and it's an example of a differential complex, but for any dimension on a manifold, no metric needed. And it has the property that this first part captures, so you can say that if such a thing is exact, means kernel of this is equal to the image of the previous one. So exact, so that kernel of the next one modulo the image of the previous one. This is called the cohomology, and that captures the topology of the domain. It's very important for solving PDEs when you have non-trivial topology like holes and tubes and things like cavities. So at the first location, it captures uniqueness of solutions. In the last place, it captures the existence of solutions. For everything, you can find something: surjectivity, injectivity, and then exactness at other places captures topological properties. So those are all structures that the thing that we have defined is able to preserve. So one has proper cohomology structure in this algebraic discrete versions that we are doing. Yes.
Excuse me, I have a basic question of definition for the cup product.
Yeah.
Maybe I wasn't
listening.
So the cup product alpha cup beta is equal to, I mean, applied to 0, 1, 2.
Yeah.
So you just take alpha applied to the first
two.
The first two, because alpha is one form, so you need 2.
That's right.
And then you beta in the following.
And then beta goes to the 1, 2. Yeah. And then you do it for all permutations of 0, 1, 2. Okay. And put in the sign.
Yes. And so on the example with F alpha,
yeah,
you have a minus coming from the sign of pi.
Yeah, because and 1, 0 is...
And there is another minus here.
Yeah, because I switched...
For the orientation.
Right, so this is F for this one.
Yes.
This is F at 1 times alpha at 1, 0.
Yes.
Which is what I had written originally with a minus sign. Then I switched this from 1, 0 to 0, 1. And when you switch a co-chain orientation, when you switch the underlying orientation, instead of doing on 1, 0, if you do it on 0, 1, you would pick up a minus sign. Yes. So that canceled the minus sign. And then we could get it in this nice.
Thank you.
Okay. Thanks. All right. So we have the wedge, we have D. Let's do the product rule. The anti-commutativity is one has that. One thing you don't have is associativity. So let me say a few words about that and give the example that shows that you don't have associativity. So there's some deep sort of algebraic reasons that you cannot have a discrete wedge product, which is both associative and anti-commutative. And for us, because differential forms are important, we are willing to live with anti-commutativity, but no associativity. And there's no choice, unfortunately. It's some deep theorem from algebraic topology that you cannot have both. And the lack of associativity actually leads to much more, some other structures, which are called A infinity structures and C infinity structures, in which the difference, the failure of associativity is taken as an object in itself, and the failure of associativity of four things and so on. And then you build some structure that physicists seem to care about. But let me show you an example that this wedge is, the discrete wedge is not associative. And like I said, because things get spread out, this is the ultimate reason that in the discrete world, things are spread out. They're not at a point. So here's an example. You take the edge and take F and G, 0 cochains, and alpha is a 1 cochain. And so F has the value, let's say, so this is 0, 1. So let's take F to have the value, F0 is 0 and F1 is 1. And G takes the value 1 and 0. So if I now do F wedge G wedge alpha, let's say alpha just takes the value 0, 1 on this. So if I do this and evaluate this on the edge, so we know that this is just the product. And by this averaging theorem, we know that this just means take the average of this product and multiply by that value. So the average of this product will be F0 G0 plus F1 G1, and then we want to multiply it by 0, 1. But because we have picked this in a nasty way, F0 is 0 and G1 is 0, so this whole thing is 0. So the result is 0. However, if I do it the other way, so then this is the average times the value of this guy. This average is now perfectly reasonable, it's 1/2. And this is the average of G times that. So you get 1/4 of alpha 0, 1, which is not 0. So you don't have associativity, and there's nothing one can do about that. So that's why people are starting to use the word structure aware. So structure preserving is too strict a notion that you have to preserve every structure, but one is finding that in the discrete world, some structures just cannot be preserved. There are some obstructions to that. So you have to be structure aware. So you have to be aware of the structures so that you try to preserve as much as possible and then try to see why something is impossible. So the timer includes the question. It's 5 minutes before the final. Okay, so I'll have 5 minutes for questions. Okay. So we have the wedge, we have the D, we had better have the product rule. So that's important to check. So it's a fact that the discrete D and wedge do satisfy. So the product rule is also called the Leibniz rule. And instead of proving it, let me just do an example, which is very illustrative. So what would be a good example? Okay. So let's take the simplest case where F and G are both 0 cochains. So F wedge G is still a 0 cochain. So remember, wedging multiplies the indices. 0 times 0 is still 0. So you can write it as a product. The wedge is too fancy a notation in this stage, but we'll just write it as a product. So we'd like to prove that D of F wedge G is equal to d of f wedge g plus -1 to the 0 f wedge d of g. So the left hand side is, so fg is a 0 cochain, so d of that is 1 cochain, so I should tell you what its value is on an edge. So left hand side evaluated on an edge is d of fg on the edge 0, 1. So that's, I could have kept the wedge, and f wedge g on 0, 1, you will see that if you work everything out, what you'll get is f1 g1 minus f0 g0. Let's keep it simple. So there will be a, yeah, so that's it. D of fg will be fg at this point minus fg at 1 minus fg at 0, because d is just the difference. That's just a function. So that will be the left-hand side. So the first term on the right-hand side, RHS1, so that's df wedge g on 0, 1. So that's supposed to be the average of g times df. So that's f1 minus f0 times the average of g. And the second term on the right-hand side is f wedge d of g on 0, 1. So this is the average of f times the value of dg on 0, 1, which is g1 minus gz. So let's add these two and look. So we've got, let's look at the cross term. There's an f1 g0 here with a plus sign, and an f1 g0 with a minus sign. So those will cancel. There's so f1 g0 and f1 g0 here, they cancel. There's a f0 g1 with a minus sign and a f0 g1 with a plus sign. So that cross term will cancel. So what will remain is f1 g1 divided by 2 minus f0 g0 divided by 2. And here also you will have f1 g1 by 2 minus f0 g0 by 2, which will add up to exactly what you want. So indeed, the product rule is true. And if it wasn't, then I wouldn't be here talking about it. So we've got the main things taken care of. Now let's, since I have time, let me talk about a fancier structure, which is actually not so fancy in calculus. So we have calculus has chain rule and product rule. We've got the product rule. Do we have the chain rule? So it turns out chain rule has a fancier description in exterior calculus. And this description is that if you have suppose you have a manifold M and a manifold N. So think of two surfaces, if you wish, or two different surfaces, or maybe two things of different dimension, doesn't really matter. And let's say you have a smooth map. So you have to read Lee to understand what is a smooth map, but okay. So you have a smooth map between M and N. Now we don't have anything smooth. We've got these triangle meshes. We don't have any kind of differentiable structure. So what should we do about smooth maps? That's the first question. And when you do something about it, what you will find is that these are the properties that are super important. So this is what chain rule is. And another thing that's important is that so this star notation is the pullback. So P star is called the pullback, and it allows you to pull back forms from here to here. For functions, it's just a composition. And so basically what it does is, if you have a form here, it allows you to define a form here. And the way you do it is you say, okay, what is the value of this form? So you take the differential of that and send the vertices, so send the vectors over there and measure the value and say, that's my value. But it's not worth it to go into the formal definition. But the main point is that it has this structure that pullback commutes with D and it commutes with the wedge product. So let me try to say, what should we use so here phi was smooth for manifolds. Now we have simplicial complexes. What should we use to play the role of smooth maps? So it turns out that slowly one discovers that this idea of simplicial maps, which plays the role of, in the discrete world, it plays the role of smooth maps. And it turns out to have this property that it commutes with D and with wedge. And it's also kind of intuitively reasonable that one should call. So what is a simplicial map is what I should tell you. So simplicial map is something you define using maps of vertices. So you say this vertex goes to that vertex, this vertex goes to that vertex. And but it should have a property. And the property is that if you have a simplex on the left, its image should be a simplex. So it's defined using a vertex map. And yeah, I won't write down the definition, but basically, so define using a vertex map, which tells you which vertex goes to which vertex. And this should be a map. The resulting map should be such that the image of a simplex is a simplex. You're allowed to collapse things. So maybe best thing is to give you an example of something which is a simplicial map and something which is not. So let's take these two simplices, so simplicial complexes. So this is X, this is Y. Let's call this U0, U1, U2, and V0, V1. And I'll define this map such that 2 goes to 0 and everything else goes to its own. So U0 goes to V0, U1 goes to V1, but U2 goes to V0. So it collapses this edge. So this is a valid simplicial map because any simplex here will be a simplex here. Either it will be collapsed into a vertex, the triangle will collapse into the edge, some edges will collapse to vertex, some edges will remain edges. So this is a perfectly decent simplicial map. Here's another one, which is not. So same guy and the same, so this is our X, and let's use the same map. In fact, no, let's use the identity map. So now even U2 goes to V2 and the other, in fact, let's just write it as UI goes to VI. And here we have this. So this is V0, V1, and V2. So this maps this vertex to this vertex, that vertex to that vertex, this vertex to this vertex. So that's your vertex map. But it's not a simplicial map because this thing, which is an edge here, doesn't map to an edge. So looking at this picture, I hope you think that, okay, this looks like a reasonable definition, at least of continuity in the discrete sense. Things that were nearby, i.e. connected by an edge, cannot get far away, but things can collapse. So this is our discrete notion of a smooth map, so to speak, in the discrete world. And how should we define the pullback? So the pullback is defined in a very simple way. So first you have this map P sharp, which maps chains to chains. And so what this does is that if you have, so phi sharp, so we first define it on a simplex, phi sharp of, let's say V0 through Vk, this will be the phi map of V0, the vertex map, see where vertex V0 goes, see where all the vertices go. And it is this if all are distinct. and it's 0 otherwise. So if there is a collapse, this phi sharp gives you 0. And if all of those go to a unique place, then you get that simplex. So this map, then you can define on any chain because you have it on a simplex, so you can take linear combinations defined by linearity. So you have this map, and you say, okay, the pullback of, so let's say you have a cochain on the right. So this is y, this is x. So in a valid simplicial map, so we'll say a pullback of alpha. I should tell you how it works on a chain. Well, it's just defined to be the value of alpha on P sharp of the chain. So let's do an example on this thing, which was actually a valid guy. So let's take this example, V0, U0, U1, U2, and V0, V1. Let's say we have a one cochain here. So this is our Y, this is our X, and this is U2 goes to V0, the others go to, U0 goes to V0, U1 goes to V1. So you take one cochain here, let's say it takes the value alpha 0, 1. So what is its pullback? Its pullback will be, so the pullback of alpha, this will be a cochain, sorry, this should be Y. You have something on the right and you're pulling it back here. And so I should be able to tell you what its values are. So what is its value on U0, U1? You just map these guys. So U0 goes via phi to V0 and U1 goes to V1, and they are distinct, so we can retain them. And so this is V0, V1, which is just alpha 0, 1. So when you pull back, let's give orientations. When you pull back this cochain, you get this number here. Let's see what happens on U1, U2. Well, that's alpha on U1 goes to V1, U2 goes to V0. That's still a valid thing, but now the orientation got flipped. So this will be minus alpha 0, 1. So on this, we get minus alpha 0, 1. How about this one? Well, because U2 goes to 0, V0, U0 goes to V0, there's a collapse. So this goes to 0. So this is the value of alpha on 0, which is 0. So this value is 0. So you basically paste the values on the uncollapsed thing, taking into account the orientation properly, and the collapsed things become 0. And this is enough to do the final example, which is to show you in an example that, so first proposition, the discrete D and wedge commute with pullback under simplicial maps. And an example of this is, let's try to do, right, so we'll take the same guy, U0, U1, U2. That's our X, that's our Y, and the same simplicial map. U2 goes. So what we'd like to do is to define, let's take a one cochain here. Oh, sorry, 0 cochain. And we'd like to prove that D commutes with pullback. So we'd like to show that if I compute D of F on the right-hand side and pull it back, that should be equal to the D of the pullback. So this is what we are trying to check. So what's the right-hand side? Well, you first compute the pullback of F. F takes values 0 here, F0 and F1. So you just paste the values. So since U0 goes to V0, you pick up value F0 here, F1 here. Since this goes to V0, this picks up that value. So you've got, this is the pullback. This is the pullback of F that I just drew. And the D of that will be, let's take the orientations. The D will be the differences. So it will be F0 minus F1 here. F1 minus F0 here, and F0 minus F0, which is 0 here. So that's what the right-hand side looks like. So this is a picture of the right-hand side. This is D of the pullback. The left-hand side should be pullback of the DF. What's DF here? It's F1 minus F0. So how do you pull it back? We've already done that. When you pull it back, this value is pasted here. Well, that matches. This value is pasted here with a negative sign from that picture. So that matches. And this value goes to 0, which matches. So we've computed the pullback of D of F and D of the pullback of F and found that they are the same. And okay, looking ahead. So next time I would like to bring in the metric. So we'll bring in metric. And to do this discretely will require something called dual cell complex. So in some sense, DEC can be viewed as finite elements, finite difference, finite volume. You'll see features of those. And I will at least make an explicit connection with finite elements in the next lecture. So metric will need a dual cell complex. This will allow us to define a discrete Hodge star, which is a very important operation that often is not taught in manifold courses because you run out of time after you have spent half a semester defining what a manifold is. So then you don't get to do fun things like PDEs. So with this, we will be able to define a co-differential, which is the dual of the exterior derivative, the L2 dual of the exterior derivative. And then with that, we'll be able to define the Hodge Laplace operator, which generalizes the Laplacian, the scalar and vector Laplacians, actually more than that in any dimension. And in fact, all linearized physical theories have this kind of a Laplacian structure, even though it's not technically a Laplacian. So we will try to see some of that in the last lecture. And so then I'll try to connect this to a mixed formulation of the Hodge Laplace problem in finite element exterior calculus. And I'll show you what Whitney forms are, because that's the shape functions which allow you to interpolate and compute errors. So Hodge Laplace problem, phi, this, and then some other operators in DEC which use this surprisingly, contraction and Lie derivative. So Lie derivative is something that you need to discretize the U dot nabla U operator in Navier-Stokes. And Lie derivative can be written in terms of contraction by something called the Cartan formula. And the Cartan formula involves contraction. So you need to understand what is a contraction. So with that, we actually have used that in a paper on Navier-Stokes on surfaces, on simplicial surfaces, which is in JCP. And the third lecture will be about differential geometry, where we'll extend this to not real valued, but vector valued. And then in the end, if there is time, I'll show something which is very modern and very popular right now in the finite element circles, where you can derive different complexes, like for the biharmonic equation, for elasticity, linearized elasticity, both the dislocation defect version. So I'm not an expert in that, but I'll tell you what I know if there is time at the end. Okay, so let me stop here.
Let's thank Anil. We'll